Welcome to today's webinar brought to you by InfoQ and Lightbend. Jonas Bonér is here to provide an architect's guide to elasticity. There are many external factors that affect elasticity, from user traffic and workload variations to networking and hardware failures. He'll discuss the pros and cons of common approaches like database replication, the different levels of elasticity. Jonas will also delve into the science behind elasticity and the practical implications of various technology and architecture choices. Now, before we get into the presentation, we have a couple of quick questions for the audience. So there should be a poll coming up on your screen pretty soon. The first question we want to know is, how would you describe your level of elasticity in your most important applications? From more than enough to the right amount, big spikes are going to kill us, it's fine, but it's expensive, or we are struggling a lot. So give everyone about 30 seconds or so to respond to that. Okay, so no one says they have more than enough. It's a good variety there, all over the board. So hopefully some information today about what's going to be helpful in your journey. The next question we have is coming up soon. What methods are you using to improve elasticity? Do you add more compute? Do you add more database? Do you have an in-memory database, distributed cache, or something else? All right, yeah, throw more hardware at it. The more compute, and definitely caching is a good solution. So there's some other options here, and I think you'll see Jonas talking about some of the different ways you can take care of that. So let me introduce Jonas. He's the co-founder and CTO of Lightbend, a distributed systems innovator and an open source community leader. He wrote the Reactive Manifesto, Reactive Principles, and numerous design books that set the foundation for how distributed systems are built today. He's the originator of Akka, a leading solution for building, operating, and securing distributed applications. Jonas is an amateur jazz musician. I noticed the guitars and the piano behind him, and a passionate skier who holds a Bachelor of Science from Mid-Sweden University. So Jonas, please take it away.
Thanks a lot, Thomas. I'm pleased to be here, and for the next 30 minutes or so, I'm going to try to walk you guys through what I think one need to think about, or some of the things one need to think about when designing for elasticity, and how to think about elasticity and the things that matters, including some of the barriers to elasticity. It won't, of course, be complete. You know, there are a ton of stuff that I'm naturally had to omit, but hopefully it will give you at least some taste of how I think about the problem and how we solve it, with the Lightbend and how Akka users have been solving this problem for about 15 years now. So okay, so first, elasticity sits sort of in a context of course, and you can say that the overarching goal that everyone wants to achieve, apart from world peace and etc. It's really to be able to stay responsive, and responsive applications really need to react to change. I think that's the fundamental underlying principle here. Being able to write applications that can adapt, gracefully, adapt to changing environments, varying demand, etc. And elasticity sits underneath at least the way I see it, underneath the overarching goal of actually staying responsive at all times. So I've broken down the three underlying traits to staying responsive Elasticity is one of them, but all of these are of course intertwined and support and are affected by each other. So elasticity means that we are able to respond to changes in workloads, meaning spikes. When I started, people, writing software, people said you got slashed audit. It was the most famous website there. I mean, you old timers can probably remember that. But what we meant that, when there's some sort of unexpected event that drives a lot of traffic to your website. These unexpected spikes are very hard to deal with because they can't be planned for. Really, it needs to be inherent design in the application to be able to cope with those types of changes in spikes. But equally important is to be able to change, or actually react to idleness. Meaning if the usage of your application goes down, you can't sit on idle hardware. Or you can, but it's very inefficient and very costly to sit on more hardware resources, whatever it is, than you actually need. So the system needs to be able to scale up and scale down depending on how it's being used. And another thing that's also sort of really ties into elasticity is how we today can deal with ensuring that we can serve customers, as close to where they are as absolutely possible. So geographic user location matters as well a lot. Being able to move data and compute into where the customer is actually physically located, and have all these three: user, data, and compute, ideally, physically co-located together. And if you have that at all times, and can adapt according to where the customer currently is and where things currently are moving, and these things can change, over the course of the life cycle of an application and how it's actually being used. But if you're able to do that, then you can serve your customers with the lowest response time at all times. The other thing, or the two other traits, I won't go into detail into those in this presentation because it will be too long, but that's DevOps agility, being able to react to things like new versions, schema changes, maintenance, and so on, and resilience, of course. I had a talk a long time ago that was titled, without resilience, nothing else matters. And what I meant by that is, is that if your system isn't up, if it's actually not running or able to serve your customers, it doesn't matter how elastic it is. It doesn't matter how beautiful it is. It doesn't matter how whatever it is. It needs to be up in order to serve your customers. And so it really starts and ends with resilience, availability. I really think. But in this presentation, I will double down on elasticity. So what does elastic means? Merriam-Webster defines it as capable of ready change or easy expansion and contraction. And it's really about being able to, as I said, being able to stay responsive and under any external factor, being able to react to changes, increases or decreasing the allocated resources to serve your users at any point in time, and ideally at any point in time have the optimal resources ready to go. Not more, not less. And elastic also means really by being able to sort of stretch out the application across multiple of these resources. Can be cores, can be nodes, can be data centers, even multiple clouds. And it's really three. We need sort of three solutions to elasticity. Workload, being able to scale up and down compute, scale in and out servers, scale data, being able to sort of address varying workloads, as I said. We also need to be able to stay responsive under operations, meaning operations might have to sometimes plan, sometimes unplanned, and be able to rebalance and repartition workloads and so on, and ensure that there's really no downtime as we do upgrades, as we do schema changes and maintenance in general. And finally, being elastic under failures. This means like be able to in the event of failure, being able to recover quickly, move workloads to healthy nodes, and replicate workloads. So we always have enough resources available to serve our customers even when things are failing. So I'm just bringing this up, so you can really understand that elasticity is really all connected, both to operations and failure management, resilience in general. It's in my experience, it's really there are a few. This is by no means an exhaustive list, but there are a few elasticity barriers that most companies or programmers run into when they're trying to build a really scalable and elastic distributed system. And first I want to say that in my experience, elastic cloud infrastructure does not directly translate to application elasticity. Elastic cloud infrastructure is great and it's really important as a backbone, and you can use it efficiently and great if you sort of know what you're doing up at the application layer. But it really goes hand in hand. There's no such thing as you can just take an existing application, throw it into Kubernetes, scaling out on Docker, and expect to have great results. It really goes hand in hand that you can think about how to design for elasticity and how making the most out of this elastic cloud infrastructure that we all have under our fingertips today in all the cloud providers. So one can really run into different sort of barriers to elasticity, and development and operations are sort of forced to rethink and rewrite often, unless you knew everything you knew when you started writing the applications, which is very seldom true. As things evolve, you need to be able to adapt to how your customers are using it, or to new features, requests, or whatever, or the actual popularity of the application. So the first one is to watch out for compute saturation. In the poll that we did in the beginning, it was clear that a lot of people were sort of really trying to address this elasticity by throwing more compute onto the problem, and that's usually the first barrier. What I mean here is that when you're compute bound, and as a result you have really poor resource utilization, and that's often due to contention on shared states, shared resources, and buying a beefier machine, sure, it can help, but it's a cap. You can't scale up the machine in more than to a specific limit, so you can only buy so much. The second thing to watch out for is I/O saturation, and that often translates, of course, to database saturation, but it doesn't necessarily have to be only that. And database and I/O saturation is really often caused by using blocking I/O and using like synchronous RPC, synchronous messaging, and so on. And sort of many high compute applications can if you run into this and not are able to address it, means that many sort of high compute applications can really run idle because the database is fully saturated. And of course, we can yet again buy a beefier database here, so scale up the database, but that will hit the ceiling fairly quickly as well. The third thing we need to watch out for is what I call connection saturation, and it's not the best term, but what I mean by that is that as you add more compute nodes, you often run into sort of a point where more compute nodes sort of yield diminishing returns, simply because even though you're adding more hardware resources, the communication and the replication between them can often eat up the value of all these new resources. So the question is then, how do you efficiently scale in and out, and how are you able to do replication in an efficient way that doesn't saturate that? And the fourth one is is really, how can we manage things like, disaster recovery? How can we stretch out our application across multiple regions? Run multi-cloud, run hybrid cloud, and so on. And this often ties into things like regulations, and security, and government demands, and so on like we're seeing a lot happening in Europe lately. So all of these things are hard challenges, both for developers and for operations to manage. So the thing is that most problems here revolve around data and how we manage and are able to efficiently replicate and work with distributed data. Because of course, I mean, if you need an elasticity, so I assume that you're writing a distributed application. And database replication, the thing that you often run underneath, that often imposes application and operations limits. The most common approach is often to just escape. Let's just distribute the database to some extent. And here we have sort of three different archetypes. We first have physical replication, meaning replication of binary data at the infrastructure level. I mean, this can, some of the things that you might run into here that's hard is like things like, how do we do rolling upgrades? How can we escape that this sort of, how can we sort of work efficiently with this sort of black box that binary physical replication means? The second one is like logical replication, and that is at the database level, is the infrastructure level. Here we have things like DML replication, and DML means data modification language. And some of the problems here are around how do you deal with like non-deterministic statements, for example, when we can't do DDL replication, meaning schema replication. How can we work with things like schema changes, and really replicate things like views? Large objects is often a problem here, so like sequences and so on. Thirdly, we have schema replication, and that can be sometimes, it has a lot of benefits, of course, but it can also be very hard to operate, because it's sometimes, you can run into situations where it actually modifies the application behavior. So it's not always completely transparent. You can run into things like consistency conflicts and different replicas and so on. So in my experience, it's better to not distribute the database, the thing, underneath the application, but actually distribute the data itself. Let the in-memory state be the source of truth, and work work with replication, distribution of data in a way that's application and domain aware, that sort of understands the semantics of the application, that understands the application that you're actually building on, what the user expects in terms of guarantees and correctness and safety and all of those things. So I'll talk more about that in a second. So, but if we'll sort of, take yet another step down into first principles and look at what are the actually things that we need to address as a programmer to tackle elasticity. The first one is contention. Contention is really the main enemy to elasticity. And when I say contention, I mean contention on shared resources in the system. It's usually the biggest scalability performance killer there is. And I'm talking here about asynchronous and non-blocking execution and I/O. Leaning towards using async and non-blocking execution and I/O. What this gives you, is the option to sort of escape hatch away from contention, giving the caller a way to sort of perform work asynchronously, instead of sort of lining up in a queue here and being blocked on the resources, for someone else to use it and then making it available. And so this can give you, a lot more efficient use of these resources. It can be more cost efficient. It can be more energy efficient. In practice, this is usually achieved by sort of allowing the caller simply to put a request on a queue, but then register a callback to say, okay, whenever my request is processed and I get a response back, notify me on this. And so the only thing that the caller needs to do is that, you know, put the request on the queue, register the callback, and then exit immediately, and then continue execution with whatever next he wants or she, I mean, it wants to do. And you know, this gives you a really good foundation for being able to also partition your data. If you think about how you should model the data to fit this well, you know, you can partition, you know, your data into smaller data sets, you know, and that also gives you a way to minimize contention, because the larger the data sets, you know, the more sort of callers are probably going to want to access that specific data set, and that leads to higher contention. Instead of, if you're able to split it up, you know, through partitioning, sharding, and so on, you're able to really parallelize out requests. So contention, you know, as I hinted out in the beginning, can in the worst case, you know, give diminishing returns. But another thing to talk about is incoherency. That can actually give negative results. I mean, here is a graph, you know, of the result of Amdahl's law, and you know, and so there are two different concepts here. I mean, so we have contention that I talked about. You know, that's really waiting for shared resources to become available. But then you also have coherency, and that is the delay for the data to become consistent. And Amdahl's law, as we can see here, really shows you, and through Amdahl's law, you're really able to model how contention affects parallelized systems. And as you can see here, you know, that after you hit a specific threshold, it will start flattening out, meaning the speed up of your system as you add cores. You know, you have cores on the horizontal axis and speed up on the vertical axis, and so it doesn't matter, you know, as how much more resources you add. When you actually hit the ceiling on Amdahl's law, you know it's you know, you sort of exhausted what you can do, regardless how many more resources you're adding. But this is not all of the truth, you know. The whole truth is actually explained through what is called the universal scalability law, that adds coherency to the problem. And when you add coherency, meaning the delay for data to become consistent, you can actually end up with negative results. That as you add more resources, meaning more concurrency to the system, the throughput actually decreases. So this is really important to think about and understand and be able to model. So you know, in essence, we need systems that are decoupled in time. You know, decoupling in time is really what gives us concurrency. It adds this sort of asynchronous boundary between components, and gives us loose coupling that we can, you know, use for a lot of other good reasons as well. You know, resilience, you know, failure management, and so on. You know, being able to bulkhead in the processing or bulkhead failures, so it doesn't lead to cascading failures. But we also need to be able to decouple our systems in space, and decoupling in space is what gives us distribution, meaning that we have a way to communicate across context. Meaning context here, you know, can be cores, can be nodes, can be data centers, and so on. And it's really decoupling in space that enables things like mobility, location transparency, as we're going to talk about more later. You know, and as I said, you know, it really gives us a foundation for resilience through bulkheading and making sure that failures don't spread, you know, randomly across the system, but you can contain them and work with them right where they happen. But these two are really the foundation for elasticity. And I mean, this might be a contentious one. Hopefully not today, but when I started talking about it a decade ago, it really was. And that is that I strongly believe the strong consistency is the wrong default in distributed systems. You know, I mean, strong consistency is most often used just out of habit, And it's how we're used to build systems. If we're coming from a centralized database world, or even more like centralized database world with a monolith on top. But so it's often like used just out of habit and out of inertia. You know, it's like the way we've always thought about it. And sure, it simplifies things, but the problem is that strong consistency, it adds contention, it adds wait time, and it's often just too brittle. It can't really be made available and be made resilient. You know, as Pat Helen said, this is actually 2 quotes from 2 different papers. The first one is like, developers simply don't implement large-scale applications assuming distributed transactions, meaning ACID, you know, meaning linearizability is sort of the technical term here. And the other one, you know, that he said that is a two-phase commit is the anti-availability protocol. And it's really nothing to be surprised about, I think, because it's really, strong consistency is really not how the world works. You know, if we just take a step back and think about how reality really works, you know, nothing is truly strongly consistent. Everything is happening sort of in a way message-based, asynchronous communication. Even how I relay like information to you guys now, you know, these are one-way dialogue we're having right now. It's really all happening asynchronously. Strong consistency is just developer convenience, but the problem is that it's, you know, so it is an abstraction, but the problem is that it's often a leaky abstraction, an abstraction that leaks just sometimes too much to be useful in all situations. But don't get me wrong, you know, it's really nothing wrong with strong consistency. In an ideal world, it would be what we all use all the time, because it's great. It's really a useful tool. It simplifies things for us as developers. I just think it's a wrong default. So we need to use it carefully and deliberately. And we know, and this is the data set that absolutely needs to be strongly consistent. Okay, fine, lean into that and use it for that data set, not having it's like this blanket that we just put on all of our data. I hope I'm making sense here. Because the problem is that we don't want to carry around more guarantees than we absolutely need. And here I'm talking about like strong guarantees on data. Because each guarantee that we add has a price that we have to pay. A price we have to pay in terms of scalability, in terms of resilience, in terms of reliability, in terms of availability. So it's often better to inverse that and start with the weakest guarantees that can solve the problem, and then add in stronger guarantees as needed. Okay. The truth, if you look at a distributed system, at least the way I view it, you know, the truth is actually that a distributed system is really a never-ending stream towards convergence. The distributed system is always, you know, in the process of convergence. It never ever reaches sort of the final state of convergence. Yeah. So we can safely assume that we will never ever reach convergence, and if we do, it's often for just brief moments in time. So the system is in constant motion, in constant sort of state of change, and in a way, you can think about it as it's always just trying to catch up. And you know, the one sort of fundamental truth that I've learned the hard way is really that there is no now. I mean, what I mean by that is there's no globally consistent now, globally consistent present. You know, it's really, as the expression goes, like it's all in the eye of the beholder. It's all relative. And you know, we need to tackle that. I think we need to think in terms of consistency, boundaries. We need to decompose the systems, so the system into this like small islands of strong consistency in this like river of constant change and this river of constant uncertainty, really. The question is then, how do we model this? I think we need to craft these autonomous islands of determinism and strong consistency, as I said. And if we're able to do so, I mean, then we can sort of, within each island, we can sort of live happily under this sort of illusion, but in an illusion that works, you know, that time is absolute, that there is a single present, a single now, and that the world inside of our on our small island is actually deterministic. you know. So the thing is that within this consistency boundary, we can really have strong consistency. We can have an atomic view of the state in our little island. And but the key here is that it really requires us to ensure that we own data. Each service or whatever it is, how you model these islands, own its data exclusively. Data can't leak. You can share data, mutable state, and so on. I'll get in more into this in just a second. And sort of good tools to think about and model this are things like bounded context from domain-driven design, for example. Microservices is of course a good way of managing this, like things like entities and aggregate roots, actors. There are many ways that you can model this. But the key is that doing it this way allows us to have strong consistency, sort of the illusion of strong consistency within our consistency boundary. Okay, but in between these consistency boundaries, we have to rely on eventual consistency. And as I said before, we shouldn't be surprised about that, because it's really how the world actually works. We shouldn't fight reality. I think it's often better to embrace it and try to model systems that actually mimics how the world actually works. And Pat Helland, the famous computer scientist, he's been talking about this a lot, and he has this paper where he defines a very nice sort of conceptual model how to think about consistency in distributed systems, where we have sort of inside data. That is what he calls, our current local present. That's our state. That's sort of inside the consistency boundary. Okay. Then we have outside data. That is what he calls blast from the past. That's our facts or events that sort of arrive from the outside into our consistency boundary. It's more or less old data. Since things are not strongly consistent between our sort of consistency boundaries. So it's always arrives from the past, And then between the services, it's what he calls almost poetic, hope for the future. That's our commands, our request. It's when someone is asking someone else to do something. It's really hope for the future because it can, commands and requests can always be rejected, etc. And they can get dropped. They can be network failures. They might never make it to the recipient. Content can be garbled along the way, etc. So I really think that shared mutable state, which is unfortunately the norm still, can be very problematic. And the reason is that mutable state is really update in place. You have your value here, and then you just change it. You have a bucket with your value, and then you just replace that bucket with something else. If you then share that bucket with this mutable state outside your consistency boundary, that means that others can't just use that safely. You need to add concurrency mechanisms to guard the data. It means increased contention. It needs increased coordination, wait time, which means that availability, scalability will sacrifice, and so on. And so we really need to contain mutable state, and we need to make it sort of non-observable to the rest of the world. We really need to sort of contain it, inside our consistency boundary, and only use mutable state for local computations. Okay. Instead, what I think we should do is that we should publish facts. So let's say you're using mutable state within your consistency boundary, within your microservice or whatever it is. And you do some processing, running your business logic, updating this state. When we're done with that processing, and we're ready to tell the world about our results, then we create an immutable value based on the result. An immutable value means that something that can't be changed, and then we publish that as a fact. This is what happened. This is something then that others then can base reason, can sort of reason safely on, because if they sort of pick up that event and that fact, they know it's a stable value. It won't just change when it's looked at. It doesn't need to be guarded and so on. And it's also a really good way to sort of track history, track causality, and so on. As I'll talk about in a second, it gives us a foundation for also doing things like understanding history. How did a component end up in the state it currently is? If we're able to actually track the state changes that led up to that, sort of this trail of facts that leading up to the latest result, you're able to understand how the system, why the system is in the state it currently is. So, and another really important tool is to leverage location transparency. And location transparency sort of assumes asynchronous message passing, but really location transparency can really give us one communication abstraction across all dimensions of scale. And what I mean by that is that we have, if our programming model or our tools support full location transparency, then we have unified semantics of how we can work with data and work with communication, regardless how the system is currently deployed or currently what topology it currently has. And that's very important in a dynamic system, since that might change. So the thing is that instead of relying on different tools with different semantics for each level of scale, meaning core, socket, CPU, container, server, rack, data center, region, or global, we can rely on one unified abstraction across all of these things. Instead of what we often do, we use different tools for each one of these levels. Like, for example, we're running on a single core, then we can use callbacks. We're running multiple cores, and we use threads and locks. If we want to communicate across nodes or regions or so on, then we use messaging, etc. If we are able to unify all this, which I think can be unified through asynchronous message passing, then we really get location transparency, meaning we have one way of communicating, regardless if you're communicating across cores, across sockets, across containers, across servers, across regions. It's all the same, and that frees up a ton of things. It frees up our mental capacity, of course, but it also liberates the runtime to do a ton of things more freely, and are able to optimize things, move data around and move components around, because nothing will break as things move across all of these dimensions of scale, even physically, geographically, and so on. I hope I'm making a little bit of sense here. The key here, is really to make distribution and the network explicit, first class. A lot of programming models in the past, like RPC or EJBs or CORBA, whatever, they've really been trying to hide the network, hide distribution, and making it feel like you're all communicating just, single-threaded, that it's all just method calls. And that's a beautiful goal, but I think it really doesn't work well in real life. So I really think that we need to distribute data and logic together. And here I'm going to talk a little bit about how we use this in Akka, sort of as a template for how things can be done here. So we have three important principles here. First, I think it's really important to sort of bundle logic and state. I've talked about this in the past, or a few slides back. That we have that states is being able to embed it as sort of an in-memory database inside each service. That means that the app itself is the service of record. It's not the database, So it's really, if we were able to achieve that, we can really distribute the data up on the app in the app tier instead of down at the database or the infrastructure level. And it gives us really full consistency boundary. In ACA we map this to actors, but you can map them to whatever that ensures those guarantees. But if you're able to do this, we can really get location transparency, like data local compliance and things like that, and we're able to actually have each service, since the data is the service and the service record is embedded in each service itself. We're able to move that to wherever we need, meaning closer to the end user if necessary, out at the edge of the network, for lower latency, for better availability, and so on. The second thing is being able to have each node, serving both reads and writes, having no special nodes, really leaning into full decentralization and peer-to-peer. Because if all nodes are equal, you have a much easier way to change the topology of the application and scale things out as needed. And finally, being able to execute this across multiple, sort of hybrid environments, meaning multi-cloud environments, in a cloud region, and multiple data centers and so on. So the backbone for how we do it in ACA, but also that's really have penetrated the industry at large, is to rely on event-driven architecture, and so the backbone for working with data in an event-driven architecture is to lean into event-based persistence, and the best pattern for that, I think, is event sourcing. Which means essentially that you have an event store, and some of the things it avoids is this problem with mutable state and update in place. And it works that you log each state change. As I said before, you create a fact out of each state change, and you log them in the order they are created, which means that you have the full history of everything that ever happened in the application or in each specific service. So this can really sort of serve as an in-memory database for each service, and it really is a way of implementing this consistency boundary where you have strong consistency with each insert in each service, and you have eventual consistency between. And relying on event logging like this, that means, as I said, you capture each state as a fact and you store the event in a log. And in a way, this sort of inverts the database application, the way how you think about the database and on how you use the database. And what I mean by that is that the in-memory representation in each service really is the source of truth. You can hit it and be sure that it's always correct, because it is truly your source of truth. It's really like in having a small in-memory database in each service. The storage, however, almost becomes like the cache. You only use the storage, sort of the storage, when you want to replay things. Replay for failure, bringing the component back up to speed after failure. Replay for replication. Replay for doing auditing and so on. And it really gives you the benefits of having one source of truth with all history, and it also gives you, from a developer perspective, a very good way of sort of avoiding this infamous, object relational mismatch, because you can work with your in-memory data, just as you have designed it to be optimally used inside each service. Whatever it is, like hash maps or vectors, or whatever it is, you can really work with your domain model directly instead of having to map that down to tables or columns or whatever it is. It also tends to have very good mechanical sympathy, which means that it works very well with modern hardware. Using the single writer principle, it can write fully uncontended down to storage. So a few very important patterns here is also that we need to lean into data sharding data. That means that every single service is sort of a cluster of replicas. So in a way, each service is sort of clustered from within. And here we can lean, as in ACA, for example, we leverage epidemic gossiping for doing cluster membership periods. We sort of create sort of a node ring where we shard data out on different nodes, and nodes can come and leave as you want. And we use sort of consistent hashing to spread out the data into buckets across all nodes. And if it's a miss, you know, then we do auto routing to the correct instance. Another really important thing when you have sharding in place is to be able to do data rebalancing. This means that we allow for data to join and leave, you know, and having the sort of the cluster or the data that's spread out on in this cluster automatically rebalanced as nodes come and go. You know, this is of course the foundation for elasticity, being able to, you can throw more and more resource at it and have it like evenly spread out to use those resources. And finally, it's really important to think about how we're handling queries, you know, being able to separate queries, meaning reads from writes. Because if you're able to do that, then you can actually scale reads separately from writes. You know, if you have a read mostly system, for example, you want to have more resource available for serving reads than writes, and vice versa. If you bundle it all into one single database, you know, then you're stuck into having to scale that thing out instead of being able to target, you know, each one of these very separate and very different use cases. And this is a pattern called CQRS, you know, command query segregation principle, and I won't go into detail about that. I don't really have the time, but I just want to mention it, you know. And another important thing here is that ACAPs are able to replicate and migrate really without any downtime. So you know, because you know, ops elasticity is equally important to workload elasticity. You know, we can't not think about the operations. We need to have a very easy way to upgrade and migrate without that downtime, and elasticity like fits right into this. And to help with this, you know, in ACA we have landed at 3 different sort of main replication schemes. First, we have pinned, so you can actually pin data to a specific region. That's for like data sovereignty and so on. Then we have multi-place replicated read for doing things, which allows active passive replication and for more global HA. And for some advanced use cases, you know, we also support, you know, multi-place replicated write, meaning active, allowing multiple nodes in different regions or even, you know, in different clouds to serve writes for the same service, and it will all consolidate correctly in the end. And having these things in place means that operations can really work with, you know, without reducing downtime. You know, making changes to the application and the topology easily, move from single region to multi-region. You know, turning on different replication schemes, because, you know, as I said, as the application is, you know, is evolving, it might, you know, different needs might be needed to be taken into account. So sort of using these principles, you know, we in ACA have been able to support elasticity, you know, across the whole application stack, from CPU, you know, up to the data layer, if it's event logging like we use, or others like some sort of data mesh, all the way up to the app and to the network. Meaning, for CPUs, we have to scale either up and down using actors and streaming. You know, data allows us to do automatic rebalancing and replication. Data here, I talked a little bit about event sourcing. We also have things like streaming projections and views and stuff like that. In the application layer, in having a very efficient way to do like this masterless clustering using multi-read or multi-write data. And finally, you know, being on the network level, be able to scale out geographically, being able to actually scale out the system across multiple regions and multiple data centers, you know, all the way up to multiple clouds. And I won't go into detail here, but you can see some of the stats and benchmarks that we've done lately here. But in essence, I just want to, you know, I just want to end with summarizing that I think, you know, the way, in my experience, you know, some of these principles, as I said, by no means an exhaustive list, but being able to apply these principles really gives you a solid foundation for how you can build elastic systems. You know, some of the core things are distribute the data, not the database itself. Think about how you can weave it into the application layer and have an elasticity and resilience being app aware. being aware of the semantics and how of the application and how your data is actually being used, not having like one size fits all here. Asynchronous, non-blocking, and I/O and compute and communication is extremely important, etc., etc. If you rely on these principles, they can really yield amazing results, as we've seen the last decade. Being able to remove these barriers to elasticity and scalability, and also to resilience to some extent. And tackle some of the hard challenges that we see today with data sovereignty in the cloud, and serving our customers, as efficiently with the lowest response time is absolutely possible. And finally, really being able to have very high infrastructure efficiency, which of course means a lower AWS or Google Cloud bill. So that was what I had for today. Do we have any questions?
Yeah, thanks for the presentation, Jonas. So anyone who has any questions, please feel free to put them in using the question part of the interface. I think one that comes to mind is these are all great principles. I've heard about event sourcing and CQRS. If I don't have those patterns in my system now, where would you recommend people find some place to get started with it? How do you start with this process?
Yeah, there are. I mean, you can of course implement everything from scratch yourself, but that would be insane to do today, I think, because there are many really good tools for event sourcing and CQRS. There are even specialized products for that. Like Akka is one of them. Axon is another one, and there are many others as well. And so I mean, do some research, look for products that support that well. That said, there are products, I don't want to name anyone, but that are sort of claiming to do event sourcing that doesn't necessarily do it as efficiently as possible, because it's not thought of from ground up as efficient event source or event-based persistence. So use some caution there as well, and ensure that you rely on tools that actually are suited for the job. When it comes to learning about it, I've given a bunch of talks about it. There are numerous books on the topic. I don't want to name anyone here, I mean, off the top of my head, but I mean, there's a lot of information out there for you to get started with event sourcing and CQRS. And of course, I want to say, it's like it doesn't solve all problems. It's a really foundational tool to have in the toolbox. And in my experience, it solves a ton of the problems that we see with distributed systems today in the cloud and at the edge. But for certain types of problems, there might be better solutions to doing persistence. So always be a bit skeptic, to everything new that you learn. But try to learn as much tools as possible, so you have a rich toolbox.
So one of the questions from the audience is asking about the returns you can expect for a high performance computing environment, because any abstraction like this isn't zero cost. Are there any quantitative measures you can point to?
Quantitative measures around what? Throughput, or what's the?
Well, yeah. How would you measure that this is a net gain? Because anytime you add these things, you might add more elasticity. What are the trade-offs you're going to see against that? Yeah, and how do you measure that these were worth it?
Everything has trade-offs, of course. I think the main trade-off, I'd say, using something like this is that you need to learn something new. It is that you sometimes need to throw old habits and ways of thinking out the window and learn something new and think about the problem in a different way. And that, of course, adds like mental complexity. But if you do so, I think that these principles can really give you the biggest return on your investment long term for elasticity and so on. I mean, so you can see some of the actual stats we have for running Akka, that we can easily get to like 1.5 million IOPS for a single service with 97% reads, and with 8 millisecond P99 write latency. So that's usually more than most people would need for a single service. And we've been running clusters that serves more than 100 million concurrent users with 6 millisecond read latency. And so I mean, I don't want to go too much into these things because it depends on, you want to look at the details how we ended up with these results, I suppose, or actually implement them yourself in some POC and see that these principles actually meet your specific needs, because it all matters, it all depends on the actual use case. But in our experience, in our customers, they've seen immense results, really amazing results when it comes to throughput, when it comes to serving massive amounts of data, and millions of users all running this in parallel. So it's I mean, I wouldn't talk about it like so passionately and so confidently if I didn't know that they actually work. But as I said again, it all depends. Do your research, look into these things, do POC for a specific problem. Come and talk to us if you have problems. I mean, we're here to help as well. So.
Yeah, one of the next questions is specific about sharding data. If you have really complex triggers in your database, can you even think about doing this, or is that a point where you have to start thinking about a full redesign? I think that's gonna be our last question before we have to wrap up.
Yeah, I mean, that's a very specific question. I mean, specific when it comes to the actual use case and how those triggers are implemented. It's hard to give a really solid advice just generically, I'd say. But of course, I mean, doing sharding means that you need to give up certain things. You need to be able to see your data in a different light. I mean, being able to partition it up into smaller data sets, and then you will always have the problem. Okay, how would you then stitch things back together if you need to do queries across all of these shards, for example? This is why most people are using event sourcing together with CQRS. CQRS means that, I didn't go into detail about that, but that essentially means that if you have event sourcing, then you have an event stream that you write to disk for every single service. All the events that ever happen in the system are written in order. The beauty of it, since you already have this event stream, that means that others can subscribe to this event stream. Others meaning other services, can be other systems, can be backend, backend ops systems or whatever, if you want to do auditing and stuff like that. But you can also have what I call the read side, the query side, subscribe to these events, sort of outside, so the hot path of the writes. So let's say that you have a read side, meaning some sort of query database. That can be, I mean, a regular SQL database. It can be like a graph database if you read like social networking type of stuff, or whatever, and it can be both. You can have different sort of query databases consume that stream and build up their own internal data sets. And if they then subscribe to multiple of these streams, from multiple services, they can easily do things like joins, get the full picture of everything that happened in the system across all of these shards, across all of these consistency boundaries, as I've talked about, and build up an optimal data set for reads, for doing queries. And as I said, the beauty of it is that you can have multiple of these, because not every single sort of way of thinking about doing queries fits all problems, and having flexibility here, building up different read models or query models out from the same data set can be extremely advantageous here, I think. So it's really worth thinking about CQRs as well as event sourcing. Else you will end up, if you only use event source, you will end up with isolated buckets that have really nothing to do with each other. It's really hard to do joins, and it's not usually efficient to do that in the service that wants to understand data being served from multiple other components, doing serve in memory joins and so on, and then that's like doing things that the database has, is designed for, so to speak. So that's how I think about it. I hope it makes sense.
Yeah. Well, I really got a lot out of this, Jonas. I want to thank you and Aka and Lightbend for providing this great presentation. And on behalf of InfoQ, glad everyone who was able to attend. For any attendees, if you want to go back and watch part of this video and catch up some of the details again, the recording will be available in about 24 hours. So Jonas, thanks again for giving the presentation.
Yeah, thanks a lot.
Yeah.
I appreciate it.